For problem 3, we will have quarter of a circle, x, y. Now I need a circle. This is quarter of the circle. Radius of this circle is r. Let me try it again. So this is r, and this will be my quarter of the circle. Much better. So radius of this circle is r, and charge q is uniformly spread over this quarter of a circle. We are looking for the electric field at the origin. Find the electric field created by this charge at the origin. We know what is electric field created by point charge. E is k, then magnitude of the charge, or magnitude of charge q, divided by distance between the charge and point of interest, distance r squared, and it is radially out or radially in depending on the sign of charge q. We don't have a point charge q here, we have extended charge. So I need to slice this charge q in the pieces of infinitesimally small charges to be able to apply this formula for a point charge. So I will choose infinitesimally small charge dq. This dq is located somewhere at arbitrary point, and this length is length of arc. It is infinitesimally small, and we will call it ds, where s is length of arc. S is length of arc, and it is equal to radius r times angle theta. And then ds, infinitesimally small length of arc, is radius r, that stays constant, d theta. Where theta is angle, we can introduce angle with horizontal, for example. So let's draw electric field created by this point charge, by this infinitesimally small charge dq at the origin. This is electric field. So this is just line that I try to draw to help me to find the electric field, and this is electric field. We will call it dE, dE, electric field created by infinitesimally small charge dq. So if we have infinitesimally small charge, then we can write dE as k dq divided by r squared r. What we will do, we will break dE in components. We'll find dEx and dEy, dEx and dEy. And then we will integrate over this arc quarter of a circle. What is dEx? This is my electric field. I project it on x. This is my right triangle. Let's introduce, let's say, angle theta with horizontal. Then what will be dEx? dEx will be k dq divided by distance squared. Distance between dq in this and this point is radius of this circle r, divided by r squared. This is magnitude. I need x projection. X projection, it will be this length, will be this leg of this triangle, and it is positive. I put plus, and to get x component, we multiply by cosine of this angle times cosine theta. This is my dEx, but I don't know dq. So I will keep cosine theta because we will integrate in terms of theta. We will integrate if theta angle from horizontal. It will be changing from 0 to pi over 2. We will integrate from 0 to pi over 2 in terms of angle, but I still need dq. So let's find what is dq. By definition, it is charge per unit length, which is lambda, times length of arc is ds. Charge is uniformly distributed. So lambda is just total charge q divided by length. Charge per unit length. Length is circumference, 2 pi r over 4 divided by 4, because this is quarter of a circle. So this is lambda. And now I need to write ds. What is ds? Okay, so this is my lambda. And what is ds? ds is r d theta. This is ds. Now I know what is dq. So let's bring it right here. Now I know what is dq, and I can write dex. It is k dq. So let's put dq in blue. I will use blue to write dq. It is 4q over 2 pi r d theta. This is my q, and we miss here r squared. We need still to have our, this was dq, now I'm right here, r squared, so it is 1 over r squared, and then cosine theta. Should we integrate? Let's integrate dex first, and then we will write dey. So ex will be now integral. We always work with first quadrant. I integrate from 0 to pi over 2. Let's put all constants together, first constants, and we will simplify it a little bit. So r and r will cancel out. Then 4 and 2 will leave me with 2 in numerator. So we will have k now, constants, k, that we can take out of integral. Then 2q over pi r squared, and then what is left, we have here cosine theta d theta. I will rewrite these constants. K 2q over pi r squared. Integral cosine theta d theta is sine theta. Limits are from 0 to pi over 2. So what is the final answer for ex? It is 2kq divided by pi r squared, and sine pi over 2 is 1. I can put here 1. And sine 0 is 0, so it is just 1. We can erase it. So we found out that it is 1 after I put in the limits. Now let's write dEy. dEy will be k dq over r squared. And now instead of cosine theta, for y component, we have sine theta. And y component is negative. So we don't forget to put minus here. Sine theta. This is my dEy. Now I bring here dq that we already found. So it is minus k. Then dq. Which color did we use? Blue. Okay, let's use blue again for dq. 4q divided by 2 pi r. R d theta. This is q. dq. And then I have sine theta, which I just leave. Can I put first sine theta? Oh, I forgot 1r over r squared. 1 over r squared sine theta and d theta. Actually, if just this is blue, no, this is right. So I put d theta that comes from dq. So this is our dy, and now I need to integrate. Ey is integral from 0 to pi over 2. R and R gone, 4 and 2. I have 2. So I have constants minus k 2q divided by pi r squared. I'm right here. Integral of sine theta d. Okay, let's keep it so far because we have limits here. Sine theta d theta. Constants are minus k 2q over pi r squared. What is integral sine theta d theta? Integral sine theta d theta is minus cosine theta, minus and minus plus cosine theta. The limits are from 0 to pi over 2. I have 2k q divided by pi r squared. Cosine pi over 2 is 0. Minus cosine 0 is 1. So what we have is minus 2k q divided by pi r squared. We found both x and y components of the electric field. The total electric field, net electric field at the origin will be Ex that we already found. Ex is right here. Ex Ix plus Ey that we already found. This is Iy. And Iy is negative as we expected. Magnitudes are the same. Iy component is negative. So this is our final answer.